picture this. You're standing on the floor of a cutting-edge, futuristic smart factory.
Yeah, the kind you see in those flashy corporate videos.
Right, exactly. And your eyes are instantly drawn to all the action. You've got the glowing optical sensors, the laser safety scanners, and, those massive robotic arms whipping around at blinding speeds.
It honestly feels like stepping into a science fiction film.
It really does. And it's so natural to just focus on the software, right? The artificial intelligence, the digital brains that are orchestrating this whole intricate mechanical ballet.
Right, because we get so mesmerized by the digital side of automation, we kind of just write off the physical infrastructure as, background noise.
Yeah. But today, we are stripping away the flashing lights and all those slick digital interfaces to ask a much more fundamental question, which is, what actually holds all of that incredible technology together?
Because, a brilliant piece of software cannot defy physics.
No, it definitely can't.
All those millions of calculations per second, those digital commands, they have to be executed in the real, harsh physical world.
Right.
So if a robotic arm is instructed to move to a coordinate with, say, sub-millimeter precision, the physical structure supporting it cannot have even a microfraction of give.
Which brings us to the core mission of our deep dive today. We are exploring the unsung hero of industrial robotics and automation, which is aluminium extrusion profiles.
The absolute backbone of the whole system.
Exactly. And we're drawing on some really fascinating insights from Eleanor Industries. They're a premier extrusion supplier based out of Gujarat, India. And using their expertise, we're going to get a look under the hood, or rather, I guess, at the skeleton of modern manufacturing.
It's a great way to put it, because while software updates happen in, seconds, the physical structural adaptability of these profiles is what dictates the actual evolutionary speed of a manufacturing facility.
So the hardware has to keep up with the software.
Exactly. Having a highly advanced cloud-connected AI coordinating your factory is completely useless if your physical machinery is locked in to an outdated, rigid, immovable metal framework.
That makes a lot of sense.
Yeah.
So in this deep dive, we're going to break down the actual mechanics of the extrusion process and explore why aluminium has just completely dethroned heavy welded steel on the factory floor.
It really has taken over.
Yeah. And we'll also examine the highly engineered geometric shapes that make all this modular automation possible.
Right.
Ultimately, we'll see how this seemingly simple material is shaping the massive logistics networks and material handling systems you rely on every single time you order a package.
Because the transition from legacy factory construction to this modern modular approach, it just fundamentally alters the economics of global production.
Okay, let's start with the building blocks themselves. For anyone listening who isn't a metallurgist, taking raw aluminium and turning it into a highly precise structural beam requires this thing called the extrusion process. So you take the raw material, you heat it up until it reaches a highly malleable state. It's not like a liquid puddle, but it's soft enough to yield under immense force.
Yeah, it's still solid, but very pliable.
Right. And then a massive hydraulic ram just forces that heated metal through a specially designed steel die.
The best way to visualize it, imagine an industrial-scale Play-Doh fun factory.
Oh, I love that analogy.
Right. But operating under thousands of tons of pressure. So the metal is squeezed through a shaped void, and it emerges on the other side as a continuous, perfectly formed structural beam.
Wow.
And because of the immense pressure and heat involved, the grain structure of the aluminium actually aligns.
Oh, interesting. So it changes the material itself.
Exactly. It gives these shapes incredibly consistent dimensions, serious structural rigidity, and a flawless, hardened surface quality right off the press.
Okay, let's unpack this a bit, because it sounds almost like stepping up from supergluing a plastic model airplane together to building with an infinitely reconfigurable industrial Lego set, or like an erector set.
That's a perfect comparison, because historically, if you needed to build a massive frame, say, to support a 1,000-foot conveyor belt,
Or like a heavy automotive welding robot.
right, your only real option was welded steel. You literally hauled in massive iron I-beams, fired up the cutting torches, and welded the whole thing together into a permanent monolith.
Which sounds incredibly strong, but also really permanent.
Very permanent. And that brings us to the economic reality of an industrial environment today. Downtime is the ultimate enemy.
Oh, for sure.
It is a financial black hole. So let's say consumer demand suddenly shifts, or a new product iteration drops, and you need to adjust the layout of your assembly line to accommodate a different packaging size.
Happens all the time.
Exactly. Well, if your factory is built on traditional welded steel frames, you are looking at an absolute logistical nightmare.
Because you would have to shut down production entirely just to start tearing the old line apart.
Oh, absolutely. You shut down the line, you have to bring in heavy machinery just to hold the steel in place while you cut it. And you have to apply for hot work fire safety permits because you are about to throw showers of sparks everywhere.
Oh, right. I didn't even think about the fire hazard.
Yeah, it's a huge deal. Technicians have to cut the heavy steel, grind down all the old welds, reposition the massive beams, weld them back together, and then, this is the kicker, wait for new paint to cure so it doesn't rust.
That sounds exhausting. So a simple layout reconfiguration could paralyze a production zone for what, days?
Days or even weeks, depending on the scale.
And every single minute that line isn't moving, the facility is just bleeding capital.
Exactly. Now, contrast that agonizing process with modular aluminum extrusion. These extruded profiles are designed to assemble using specialized connectors, brackets, and bolts.
So no welding.
Zero welding. If that same robotic arm needs to move 2 feet to the left for a new product run, a couple of technicians can literally just walk over with hand tools.
Wait, just hand tools?
Just hand tools. They unbolt the aluminum frame, slide the module over, and bolt it back down. The reconfiguration happens during a standard shift change. The factory doesn't miss a beat.
That is wild. The time savings alone must be massive.
Yeah.
But I imagine beyond just the operational flexibility, there's the sheer physical resilience of the material. Because industrial environments are notoriously brutal.
No, they are punishing. You are dealing with massive temperature swings, high humidity, and just constant exposure to caustic chemicals, heavy lubricants, and cutting fluids.
Which I'm guessing steel doesn't love.
Steel hates it. Welded steel is in a perpetual state of decay in those environments. It's constantly fighting rust.
Right.
But aluminium naturally oxidizes to form this microscopic protective layer that resists corrosion. So those extruded bars and struts maintain their structural integrity and their clean, sterile appearance over decades of service with virtually zero maintenance.
That is a huge advantage. But I mean, surviving a harsh chemical wash is really only half the battle. Because a structural block is entirely useless if you can't actually build complex, highly specific machinery with it.
You need versatility.
Exactly. Which brings us to the geometric shapes themselves.
Yeah.
You can't construct a multifaceted automated workstation if all your structural blocks are just, identical solid squares.
No, you definitely can't. And that's what's fascinating here. The true genius of the extrusion process is that it allows engineers to create customized cross-sections optimized for really specific mechanical tasks.
So they aren't just extruding flat bars.
Not at all. They are creating complex internal and external geometries that serve direct operational purposes.
Okay, so let's look at what is probably the undisputed workhorse of the modern factory floor, the standard T-slot aluminum profile.
Yes, the T-slot, it's everywhere.
Right. And if you look at the cross-section of a T-slot profile, it literally has grooves shaped exactly like the letter T running continuously down its entire length. And I read that this is an absolute game changer for assembly.
It changes everything because you can slide a specialized drop-in nut right into that groove at any given point along the bar, and instantly you have a high-strength, secure mounting point without ever picking up a drill.
That is so smart, because if you've ever tried to assemble like cheap flat pack furniture at home.
Oh, don't even get me started.
Right, and the pre-drilled holes are misaligned by even a millimeter. It compromises the integrity of the whole piece. Now multiply that millimeter discrepancy across a 500-foot automated conveyor moving thousands of pounds of product.
Exactly. In that setting, pre-drilled holes are a huge liability. T-slots eliminate that liability entirely. They allow for the rapid fluid installation of optical sensors, mounting plates, structural brackets, you name it.
So if you want to attach a laser scanner to monitor a conveyor, you just slide a nut into the T-slot and bolt the scanner on.
Yep. And say you test the system and realize the scanner needs to be 2 inches higher to properly read a barcode.
With steel, you'd have to drill new holes, right?
Yeah. And eventually, your frame ends up looking like Swiss cheese. But with a T-slot, you just loosen the bolt, slide the scanner up the continuous track, and lock it back down.
That level of adjustability is incredible. Now, what about applications demanding much higher tolerances? like extreme load capacities where a standard T-slot just won't cut it.
For those, engineers move away from standard T-slots to heavy-duty structural profiles.
Okay, how are those different?
They are extruded with significantly thicker outer walls and reinforced internal geometries. They form the massive machine bases and the foundational supports for really heavy stuff, like robotic stamping or milling stations.
Oh, I see.
You will also see round and square extrusions frequently combined with specialized aluminum tubes. That creates incredibly robust, seamless framework that offers specific types of torsional stability.
Okay, but there's one specific profile design we found in our research that totally changes how we think about structural engineering. And here's where it gets really interesting to me.
Oh, the pneumatic profiles.
Yes, because usually industrial pneumatics using compressed air to power actuators, grippers, and moving parts, that means relying on air compressors that pump air through a messy, chaotic spaghetti tangle of plastic hoses running all over the outside of the machine.
It's usually a complete mess.
Right, and one snagged hose on a passing forklift, and the whole robot drops its payload. But these advanced pneumatic profiles are extruded with hollow, perfectly airtight chambers built right into the metal. So the structural frame itself doubles as a functional air conduit.
It is brilliant engineering. If we connect this to the bigger picture, in traditional construction, a beam's only job is passive, right? It just sits there and holds weight.
Just fighting gravity.
Exactly. But in an advanced automation ecosystem, a structural beam is an active participant in the machinery's respiratory system.
Wow, it's respiratory system.
Yeah. The compressed air that forces a robotic hand to clamp down on a piece of metal is channeling directly through the structural support leg holding the robot up.
So the skeleton is literally functioning as the airway. That eliminates the need for external hoses, saves a massive amount of physical space on the factory floor, and completely protects the air pressure lines from environmental damage.
Or accidental severing from that forklift you mentioned. Integrating the utilities directly into the load-bearing structure represents a massive leap in material handling design.
Okay, so moving from the individual profiles to the massive systems they construct, we can really see how these shapes are assembled to replace manual labor.
And support highly complex material handling, yeah.
Right. Conveyor frame networks are a prime example here. In a global logistics facility, product movement has to be continuous. Using engineered aluminum profiles, manufacturers build rigid, highly stable frameworks that stretch for literally miles across warehouse floors.
And the modular nature of these profiles means they integrate seamlessly with the heavy drive motors, tensioned rollers, optical tracking sensors, and the local automation control units.
Everything just bolts right into those tracks.
Exactly. Automated packaging lines utilize the exact same principles. So when a facility needs to reconfigure a packaging system to handle a completely new box dimension, or, say, a different shrink wrapping mechanism, the scalable assembly configurations built from these profiles make that transition fast and relatively painless.
They also form the basis for protective enclosures and safety guards, which is huge. Because no matter how intelligent an AI system is, heavy machinery moving at high speeds poses a lethal threat to human workers.
Yeah, safety is non-negotiable. Strict industrial safety regulations require robust physical barriers.
Right. And aluminum profiles allow engineers to build massive impact-resistant safety cages. And they incorporate interlocking safety panels and electronic kill switches directly into the frame, all without adding tons of dead weight to the facility floor.
And those safety enclosures frequently utilize the exact pneumatic profiles we just discussed.
Oh, no way. Really?
Yeah. They run the airlines for automated door locks and safety control gates right through the cage's own structure.
That is so efficient. But okay, let me stop you right there. I have to push back a little on this emphasis on how lightweight these materials are, especially when we talk about robotic workstations.
Okay, let's hear it.
Well, an industrial robotic arm in an automotive plant is heavily articulated, right? It's moving at lightning speed, suddenly stopping, and swinging heavy engine blocks or car doors around.
Oh, yeah, they generate insane amounts of force.
Right. That creates a tremendous amount of kinetic energy, momentum, and violent dynamic load. If the foundation supporting that robot is a lightweight aluminum frame, wouldn't the entire structure just vibrate and shake violently?
It's a very valid concern.
Because it seems like that constant vibration would completely destroy the sub-millimeter precision the software is trying to execute.
And you're completely right. If you simply bolted a high-speed 6-axis robotic arm to a standard hollow piece of lightweight aluminum tubing, The vibration would absolutely tear the assembly apart.
Okay, so I'm not crazy.
No, not at all. Or at the very least, it would render the robot's positioning hopelessly inaccurate. But this is where the advanced engineering of the extrusion profile solves the physics problem.
Okay, how?
Manufacturers don't just extrude a simple hollow pipe. They engineer complex honeycomb-like internal webbing within the cross-section of the heavy-duty strut.
Wait, so it's not about adding brute force mass to weigh it down. It's actually about the internal architecture.
Precisely. Think about a solid block of iron. It just transfers a shockwave straight through to the concrete floor, which, by the way, eventually damages the floor and the machine.
Ouch. Yeah, that's not good.
Right. But the intricate internal webbing in these aluminum profiles actually breaks up the kinetic energy. As the robot stops suddenly, the resulting vibration is forced to dissipate across dozens of internal structural channels.
Oh, wow.
Yeah, it absorbs and dampens the dynamic load before it can reverberate back up into the robotic arm and disrupt its precision.
Okay, that makes sense. But carving out complex honeycomb structures inside a long metal tube sounds insanely expensive and difficult to scale.
It sounds like it would be, yeah.
Right. Why not just cast a solid iron base specifically for that robot? If an automation facility needs thousands of these custom vibration dampening pieces, how do they produce them economically?
So this touches on the critical pairing of the extrusion process with CNC machining.
Oh, okay.
The extrusion process itself naturally forms that continuous honeycomb cross-section along the entire length of the beam incredibly efficiently. Because remember, you only have to design the steel die once.
Right, you just push the Play-Doh through the shape.
Exactly. But to actually attach a bespoke robotic arm to that complex beam requires exact mounting interfaces. This is where CNC, which stands for Computer Numerical Control Machining, comes in.
Using computers to guide automated cutting tools with microscopic precision.
Exactly. An engineer takes that extruded honeycomb beam, and a CNC machine carves out highly specific mounting points. It mills away exact fractions of a millimeter of aluminium, so the robot's base plate locks in flawlessly.
That is incredibly precise.
It is. The software controlling the CNC machine ensures that every single cut, thread, and mounting hole is perfectly toleranced.
Which brings us to a crucial bottleneck in global automation upgrades. So what does this all mean for someone listening? If you were overseeing a warehouse automation upgrade, you might think, why not just buy standard metal bars off the internet?
That is a trap a lot of people fall into.
Right. But these structural webs and CNC cuts have to be so microscopically precise, you can't just buy generic stuff from a discount hardware supplier. The components often require unique dimensions and custom integrated channels that have to perfectly match bespoke machine configurations.
This raises an important question about load-bearing capacity and long-term durability, because a complex automation system is truly only as reliable as its foundation.
Right.
If you buy cheap, generic structural bars and the slot design or the machined mounting point is off by just a fraction of a millimeter, the kinetic energy of the robot isn't transferred properly into that dampening webbing.
Oh, so it just rattles itself to pieces.
Exactly. Over thousands of cycles, that micro-wobble amplifies, the robotic workstation fails, and your million-dollar automated cell just grinds to a halt.
This highlights exactly why partnering with specialized suppliers who possess advanced manufacturing capabilities is just non-negotiable.
It really is.
Using Eleanor Industries as an example of this domain expertise, they operate out of Ahmedabad, Gujarat, which is a rapidly expanding global hub for high-tech manufacturing.
It's booming over there.
Yeah. And the reason companies like this are critical to global supply chains isn't just because they melt metal. It's because they deploy advanced profile manufacturing machine technology that solves the scalability problem.
Because outfitting a 1 million square foot automated distribution center requires a staggering volume of custom structural profile.
I can't even imagine the scale.
A supplier must deliver massive production capacity without sacrificing dimensional accuracy or, consistent surface finish across tens of thousands of components.
Right.
You are essentially partnering with an engineering firm that helps evaluate the specific load-bearing capacity, torsional stability, and weight distribution required for your unique application before a single piece of metal is ever pushed through a die.
They ensure the custom aluminum profiles for your specific CNC machining setup, or those heavy-duty robotic mounts, won't just fit on day one, but will actually withstand years of continuous high-speed industrial vibration without degrading.
The physical infrastructure must be flawless for the digital automation to function properly. The structural foundation cannot be an afterthought.
Taking a step back, this completely changes how you view a modern warehouse or factory floor.
It really pulls back the curtain.
It does. We've explored how raw aluminium, through heat and immense pressure, is extruded into incredibly strong, highly engineered geometric shapes. We've seen how these profiles, from modular T-slots that completely eliminate drilling, to those ingenious pneumatic conduits that act as a machine's respiratory system, they've revolutionized industrial construction, replacing heavy, permanent steel with adaptable flexibility.
It's a total paradigm shift.
Without these customized vibration-dampening aluminum frameworks, the rapid evolution of robotics, vast conveyor networks, and complex material handling simply would not be physically possible. The brilliant digital brain of the smart factory relies entirely on this silent, flexible skeleton.
And, as we look toward the horizon of smart manufacturing, there is an implication of this modularity that pushes right to the edge of current technology.
Really? Like what?
Well, we've discussed how human engineers use these flexible aluminum profiles to manually adapt assembly lines. But consider the integration of artificial intelligence with real-time physical sensors.
Okay, I'm tracking.
What happens when an automated production line can monitor its own structural stress through microvibration analysis?
Wait, you're talking about the machine feeling its own fatigue?
Yes. Imagine an AI system identifying a structural weakness or a workflow inefficiency in its own physical layout. It doesn't just flag an error code for a human.
Wow.
It automatically designs a reinforced structural geometry, directly interfaces with the supplier's automated ERP system, and orders its own custom-machined aluminum extrusion upgrades without a human engineer ever getting involved.
That is incredible.
The custom parts arrive, and automated maintenance drones swap out the modular pieces.
So the AI brain is literally redesigning and upgrading its own physical skeleton in real time to keep up with production demands. No blueprints, no humans.
Exactly. Given how precise and modular these extrusion systems already are, the physical infrastructure is fully prepared for that level of autonomy.
The physical world is finally capable of adapting at the speed of the digital mind.
Exactly. It's wild to think about.
Well, you will definitely never look at the structural framework of a conveyor belt or a robotic arm the same way again. Thank you so much for joining us on this deep dive. Keep looking past the blinking lights, keep questioning how the hidden pieces fit together, and keep exploring the physical systems that make our modern world run. Until next time.